When you type a prompt into a modern AI, the experience is incredibly convincing. You receive a flawless response that feels like a sentient being. But strip away this interface, and you'll find no biological brain and no hidden database of encyclopedias. The reality is a massive, static mathematical expression. It is populated by billions of adjustable numbers, called parameters, which function like billions of independent dials on a colossal soundboard. The AI isn't contemplating thoughts. It is executing a rigid, predefined mathematical equation, processing your request through a specific arrangement of numbers to generate an output. When this network is first constructed, before it sees a single word of human text, every one of its billions of parameters is set completely at random. If you asked a question to this uncalibrated network, it would output pure, chaotic gibberish. How does this giant random math equation teach itself the complex, nuanced rules of human language? Intelligence is discovered through a relentless mathematical game of prediction. Neural networks process tokens, fragments of text converted into raw numbers, rather than concepts or ideas. During the preparation phase, developers download the public internet, strip away the formatting, and crush it into a single sequence of these tokens. This one-dimensional sequence is the only way the neural network ever experiences human knowledge. We are forcing the multidimensional internet through a single linear pipe of data. To begin calibration, we feed a small random sequence of tokens into the uncalibrated network to test its current state. It calculates a probability for the next block, but because the dials are random, its highest probability guess is entirely wrong. We then perform a reality check, looking at the actual training data to reveal what the correct next token was supposed to be. We calculate the loss, a mathematical score that measures exactly how wrong the network's prediction was. An algorithm reaches backward through the network to slightly tweak the random knobs, ensuring the correct token gets a higher probability next time. AI learning is the physical, microscopic adjustment of billions of parameters to minimize the error of a prediction. This parameter update happens across millions of tokens simultaneously in massive batches. Running this loop requires immense physical infrastructure and specialized hardware, like these NVIDIA H100 GPUs, to handle the continuous matrix math. Thousands of these machines run this prediction loop relentlessly for months on end. AI is the brute force repetition of this tiny prediction loop, executed trillions of times until the mathematical parameters perfectly mirror the statistics of human language. Eventually, the training phase ends, and the billions of parameters are permanently locked in place. The resulting model acts as a highly compressed, lossy zip file of the internet, a statistical reflection held within a fixed mathematical structure. When a user queries the AI today, the system enters the inference phase. It is no longer learning or updating. It is simply running the locked math. The model creates responses by continually flipping a statistically biased coin to select the next most likely token. The assistant on the screen is a frozen snapshot of internet statistics, endlessly tumbling tokens forward. This predictive mechanism guarantees hallucinations. The model is designed to guess plausible statistical patterns, not retrieve hard facts. The AI will confidently fabricate information if asked about obscure topics that lacked deep statistical weight during its training. The network only possesses a finite amount of computational power per token, making it terrible at complex math or character counting. If the model attempts to jump straight to a complex answer in a single step, it often fails. But spreading that computational work across multiple sequential tokens gives the network the room it needs to solve the problem accurately. This system is a statistical token tumbler. To harness its power, we must treat it strictly as a tool, provide it with specific context, and always verify its output.